Alright, we're going to be looking at some simple parallel circuits now. And one of the first things you may notice is I've changed my battery configuration. Before we had 4 cells in series, and now we've got those same 4 cells in parallel, and I've actually put in new batteries because as we're doing this, our current values are going to be drawing from our batteries pretty hot and heavy. So my point of putting my batteries in parallel isn't necessarily because we were doing a parallel resistor. It's because we need the extra current. And when we put them in series, the voltage remains, current capacity of the batteries remain whatever one battery is, but voltage increases. So when we put one battery, we have 1.5 volts. When we put 2, we have 3. When we put 3 batteries at 1.5, we have 4.5. When we put 4 in series, we have 6 volts. But they're all the same current capacity as each individual battery. But by putting them in parallel, I still only have 1.5 volts, but I have quadrupled my current capacity of what one cell would be. So that's why I chose to put them in parallel, not just because we were doing a parallel circuit. The other reason is the lower the voltage, the lower the current, and we're going to get into some fairly decent currents, not anything major, but still enough to impact us. So, I'm going to show you, first of all, that this is indeed 1.5 volts of battery, and it doesn't matter where I measure that, it's electrically the same, and that's what's happening. So now, we're going to talk about parallel circuits. Parallel circuits have some interesting characteristics just like series circuits do. In a simple parallel or any parallel branch, each resistor in that branch is going to see the same voltage value. So the voltage across R1 is the same as the voltage across R2, which is the same as R3. And that's because they're each connected to the source. Top of R1 is connected to the positive, top of R2 and the top of R3 are connected to positive. Same is true with the negative on the bottom. However, we have more than one path for current. So we'll have full current in the wire leading and returning to our source, but each branch is going to have its own individual currents, and those currents should roughly add up to whatever full current. And the reason for that is just because we're going to be pulling some fairly good current with this, and our batteries will diminish somewhat even as we're doing the experiment. So just imagine your flashlight that you had and hooking a really bright light up. You know how a flashlight will die fairly quickly, at least the old-fashioned kind before the LEDs. So kind of a similar thing here. So we may see some variance in current, but we'll be fairly close, might be a better word. Now, there's 3 resistors here, and I'm going to pick 3 at random, and you're going to do the same thing, and you're not going to use the same 3 that I did. The one thing I can tell you, if we had a 100 ohm, a 10 ohm, and a 1 ohm in this circuit, I know my overall resistance is going to be lower than my lowest, which would be 1. Now it might be significantly lower, or it might be just somewhat lower, but it's going to be lower than my lowest value. So if I had a 50, a 25, and a 15, my overall resistance would be lower than my 15. And it doesn't matter about the order. I could have a 20 here, a 15 here, and a 50 here, and it's still going to be lower than 15 because this battery doesn't see 3 resistors. It just sees an overall resistance. It doesn't know how they are or how they're configured because it's just a battery. It doesn't have any sense to know that there are 3 resistors. It just sees it as one overall resistance. And so that's the thing. Now if we want to calculate these resistances, we can do that using 2 formulas. One is product over sum. So let's say we had a 20 and a 10 here. We could take 20 times 10, which is 200, and divide it by 20 plus 10, which is 30. So if we did 200 divided by 30, we would get the equivalent resistance of just these 2. Then we would have to take that equivalent resistance and do it with R3. So it's a multi-step process doing more than 2, which is why I like this second formula better. That second formula is the reciprocal of total resistance is equal to the resistance of R1, R2, R3, and so forth and so on until you get whatever R last is. So there could be 100 of these, and you can calculate it that way. So what I would do is I would say, I would enter the value of R1, I would reciprocate it, then I would say plus, enter the value of R2, reciprocate that, enter the value of R3, reciprocate that, hit equals, and then reciprocate my answer. And on most calculators, there's a 1 over x or an x minus 1 key, and that key is what reciprocates a value. So for instance, if I had a 20 ohm and a 50 ohm and a 100 ohm, and doing this upside down should be a treat for both of us, I would hit 20 x minus 1 plus, I can't remember what values I said, but we'll say 50 x minus 1 plus 100 x minus 1, and we'll hit equals. Now we know 20, 50, and 100, it should be less than 20, and then I have to reciprocate my answer, and hit enter, and my answer is 12.5. So that holds true at least to our theory, which is if I have 100, a 50, and a 20, I'm going to be less than 20. So I can't guarantee that is the right answer, but I can guarantee it fits because of that rule. So that's how you can at least know if you're in the parameters of what can be done. So now I'm going to wire 3 resistors, and I'm going to go ahead and wire them together. And remember, a resistor doesn't have polarity. The red and the black are just a way of distinguishing what I'm doing here. And I'm looking for a couple of particular values here. Now remember, if you look, the tops of all these are electrically the same. So that's what I'm doing here, and I'm going red to red. So, whoops, that didn't work at all. Let's try that one more time. That's one of the things you have to be careful about when you're skipping one. So I'm using our unknown, which we now know is 20, a 10, and a 5, and I've got all my tops of those tied together. And just to make it quicker and less painful, I'm going to get it a little closer to me so that I can do this a little more rapidly. So there we go. Now I'm going to add a wire, and it doesn't matter where I add that wire. I can add it to any of these 3 because they're electrically the same, or I can add it to any of these 3. So I'm going to go ahead and do that before we get started, because this is the wire that will connect our source here. So obviously you needed your 4 resistors and your batteries, and I am going to use a switch just for some reasons here. Alright, so I'm going to turn that around. I'm going to turn my source around here. Now I'm going to come out of my source here. Out of my source. Or excuse me, out of my resistors, through my switch, and then into my source is what I was trying to say. So that is now connected to source, other than I haven't thrown my switch. So let me get that a little closer to you. So let's follow this path before we do it, and I just pretend the switch is closed. We're coming out of our source, and ultimately through our switch. We're going to R1, R2, and R3, or you can call that R1, R2, R3, whichever way you prefer. The essence is the same. So the source is feeding the top of R1, R2, and R3, and that's positive. And then bottoms are all tied together, and that goes back to negative. So it's exactly as our schematic is. And I'm going to close it. And we're going to read source voltage here. Source voltage is about 1.5, and you're going to see that across each of these resistors, we're reading a little bit lower, and I'll kind of explain that. And we may be able to, let's get to the actual resistor, may be able to fix some of that, because what we're doing is we're losing some voltage in these connections, and it could be through this switch. Let's see if that switch had some resistance to it the way I had it. Nope. So I don't know if we're losing it through the wire or the connections. I'm going to tighten up on them. And this is why your mileage may vary a little bit, because we do have some resistance in these leads here. So let's try that one more time. We'll read source 1.5, and we'll read across our resistors 1.3. So we're just going to, for intents and purposes, use that 1.3 value. We've got a little bit of a loss. Let's see, just for the fun of it, if it is in our switch. It could well be. Sometimes, especially this polished metal, doesn't conduct super well. So let's see if that changes it here in our. Yeah, that brought it up a little bit. So we'll do without the switch. I'll forego that. I had a reason for doing that, but that's okay. Let's not knock our meter over, and let's read current. And the way we're going to have to read current is we're going to have to break this circuit. And I know this is going to be in milliamps, but we're going to start with amps because that's just the way we should. Now remember, to read full current, I have to break one of these leads from my source. This one's closest to me. So I'm going to put my meter here, and I'm going to rejoin this path. And if I can get my meter to, and I'm on AC, so I'm going to have to change my meter to read DC milliamps. So about 0.47, so that's almost half an amp. So I want to write that down so we don't forget it. 0.47 amps. So that's 470 milliamps. So again, that's pretty good current draw, which is why I wanted to put these things in parallel to increase that current capacity. So now I'm going to disconnect my source from this side and reconnect it here. Now I want to measure my individual resistors. Now let's talk about that before we do it. Now normally I would connect this here, and it would connect this to that resistor, and this resistor. Well, I'm wanting to measure current through this resistor right here. So what I'm going to do that is I'm going to disconnect this wire right here, and I'm going to reconnect it momentarily to our source without the screwdriver getting in our way. So what's happening is our source is now going through this resistor and that resistor, but it's not going through this one because we've broken the path. So we need this connected to that, and that's exactly what we're going to use our meter to do. And we read 0.28, 0.28. So I'm going to rejoin this, as it were, and let you see it back together again. And then we've got to do something very similar for R2. So before, this was under here, connecting our source to all three. So what I'm going to do is I'm going to take this middle wire off, and I'm going to have to do some reconfiguring. Remember, it was these first two, and we can reference our black wires to remember that. So I want the middle one not connected. So I'm going to have to do this, and do this. So now current is flowing through this resistor, but not this one. So I'm going to have to reconnect this to that using my meter to read my second current draw. 0.14. So let's write that down. And now I'm going to have to do something similar for the last. And what I'm going to do is I'm going to reconnect this here. So current is still flowing through this guy, through that guy, but not through that guy. So if I can untangle my leads here, I'm going to have to reconnect it to here. And this one, be careful about decimal points, is 0.07. 0.07. And that's the first one that was a 0.0 something. Now we calculated total current, or measured, total current to be 0.47 amps. Then we measured individual currents, and they were 0.28 plus 0.14 plus 0.07, and that yields 0.49. So we're off by 2/20,000th of an amp. So that's darn close. That in the electronics world, that is very much negligible. So that worked. Now we're going to use Ohm's law to see how our actual measured goes against our theoretical. So I'm using a 20, a 10, and a 5. So I'm going to use this reciprocal formula to calculate total resistance. 20 x over 1 plus 10 x over 1 plus 5 x over 1 equals x over 1 equals 2.85 is my overall resistance. 2.85 ohms. So if you remember, and I'll put this chart out here in front of you, Ohm's law is V over I times R, and we cover up whatever we don't know. So we're wanting I, so we know V is approximately 1.5 volts. We know R is 2.85 ohms. And we have to do that math. So our V, 1.5 volts, our R, 2.85 ohms, and we will do that math on the calculator because I can't do that in my head. Let's get it backwards. 1.5 divided by 2.85. 0.52. So again, negligible. We measured 0.47. We added up our total currents. We got 0.49, and we did the theoretical, and we got 0.52. Very much negligible differences there, and in line with just what we saw here. So your job is going to be to do 3 resistors, not the 3 that I did. And you can do that any way you like as long as you're not using the exact 3 that I used. And I want you to actually, let's change that. I'm going to have you use a specific 3 because you're going to answer some questions about that. And we're going to make these values far enough apart that you should be able to get close to our answer. So I'm going to have you use the 20, the 15, and the 10. So you're going to connect the 20, the 15, and the 10. And now you know those 3 should be less than 10 ohms as a resistor. And you're going to hook them to your load, and you're going to parallel batteries just like I did because you're going to need that extra current value. And you're going to make the same measurements I did. Overall current through each of those, and answer some questions that shows your understanding of parallel branches even if you don't make the measurements. So that's going to be your experiment. So let me kind of draw those values. 20 ohm, 15 ohm, and 10 ohm. So this will be what you will configure, and again this order makes no difference, but if I ask you what is the current through the 20 ohm, you'll need to answer specifically for the 20 ohm whether it's here or here or here. And if I ask you what current for the 15 ohm is, you'll need to answer for that one whether it's here, here, or in the middle like I've got it. You get the idea. So we're going to ask you to measure total current, measure individual currents, and get an approximate value of those, find the answer based on your experiment. You're going to have to submit me a picture of your hooked up experiment and drop that in the Dropbox as well. So if you have any questions, please let me know.